configuration of endpoints in the plane where two of the points coincide. And one of the things that we saw is that that ideal is generated by all the polynomials which are alternating with respect to the action of the symmetric group permuting the point. That is, that they change sign for odd permutations. And so it's clear, at least from that description already, that this action of the symmetric group here permuting the points is somehow important in the picture. And what I'd like to do today is focus on that. And in particular, I want to discuss a little bit the ring of invariance, which turns out to be pretty easy to describe here, actually. There's not a whole lot I want to say about that. But also the ring of co-invariance, which is a slightly less well-known concept, although closely related. And I thought I would begin actually with just a review, if you will, first for those who might not be familiar with this, of some sort of general facts about rings of invariance and co-invariance for a finite group acting on a finite dimensional vector space. And then in the second part of the lecture, we'll discuss some of the special features that these have in the situation of endpoints in the plane. But at the beginning, I'd like to just go over a bit of the general theory, partly because it's interesting and partly because it kind of will motivate the ring of co-invariance and show you how some other things fit together. So for the moment, we're going to not just look at the situation of points in the plane, but something much more general, namely we'll have a finite dimensional vector space V over a field K, and we'll have a finite group G acting on V by linear automorphisms. And we're going to want to consider the situation where the representation, this is called a representation of G, a linear representation. And we want to consider the situation where linear representations break down into direct sums of irreducible ones, which means we're going to want to consider the situation where the characteristic of our field does not divide the order of the group. So this will be a sort of blanket hypothesis for us. And when this is the case, one of the basic theorems in the theory of representations is Maschke's theorem. Which says that every such V is a direct sum of irreducible representations VI. Right, so what does this mean? Well, first, V is the direct sum of subspaces VI. The VIs are G invariant, right? The elements of the group should send elements of VI back into itself. And they should be irreducible, means that they themselves contain no further proper G invariant subspaces, except, of course, for the whole space or zero. Okay, so this is sort of the fundamental fact about representation theory of finite groups in good characteristics. Now, from the point of view of geometry and algebra, an interesting thing to look at, and which was studied very extensively classically already in the 19th century, is the question of what are the polynomial functions on V that are invariant with respect to the group action. Okay, so I'll denote by C of V the algebra of polynomial functions. Oops, for the moment I want to use K, so let's say K of V. And we're going to want to look at the invariant polynomials. Okay, so this will be the ring of invariance. And it's geometrically, what's the meaning of this? If we think, well, for the moment, let's say K is algebraically closed, so we're sort of in the situation of classical algebraic geometry, then K of V is the algebra of functions on V. And what's K of V G? What's the ring of invariance? Well, if a function is G invariant, it means it's constant on every G orbit. Okay, so an invariant function really defines a function on the set of orbits. And there are always enough invariants for a finite group that you can distinguish the orbits given two separate orbits, you could find a function that's 1 on this one and 0 on that one. So you can think of these really as functions on V mod G, right? And more precisely, the algebraic variety, right, which is spec of this ring, is V mod G in a number of precise senses. For one thing, its classical points correspond one-to-one with the orbits of G and V, but also there's a sense in which it's a categorical quotient. If you have any homomorphism from V, if you have a morphism from V to any other algebraic variety where the morphism itself is invariant with respect to G, it'll factor through V mod G. Okay, so that's one way to think about the ring of invariance. A classical fact is that it's finitely generated, and I'll discuss that a little further as we go along. One way to see that it's finitely generated, and also to answer questions about what generates it, is to look at a related ring. So I want to also introduce the ring of coinvariance, and so I'll start with the ideal IG generated by all the invariant polynomials, except of course I don't want constants in an ideal, so the invariant polynomials which are homogeneous of positive degree. Okay, so I'll take the invariants which are in the homogeneous maximal ideal inside this ring of invariance, and then I'll take the ideal in the larger ring of all functions generated by that homogeneous maximal ideal in the ring of invariance. And I'll call RG the quotient of the polynomials on V mod this ideal, and this is called the ring of coinvariance. Not to be confused, by the way, with covariance, which is something else. Okay. Okay, so what's the relationship between these two things? Well, there's a famous lemma of Hilbert, which is sort of the basic key to his demonstration that this ring is finitely generated. That was Hilbert's 14th, I think, problem. So let me write that down. So Hilbert's lemma says that what generates the ring of invariance is what generates the coinvariant ideal. Okay, so to be more precise, if F1 through FR are homogeneous elements of the ring of invariance without constant terms, so of positive degree, then the ring of invariance is generated by the F's as a K-algebra if and only if the ideal is generated by the F's as an ideal. Well, and of course, this immediately implies that there's a finite set of generators. Right. Let me mention, I'm going to discuss a couple of lemmas here, so, and they all have sort of easy proofs, so let me just mention a little bit about how to see this. So first of all, this direction is trivial, because if the F's generate the ring of invariance, then every homogeneous invariant of positive degree is a polynomial in these F's without constant term. And the ideal here, by definition, is generated by those. So it's generated by the F's, because all their terms are going to have one of the F's as a factor. Right? So this is clear. And this direction, what you do is you proceed by induction on the degree, in effect. So you say, well, suppose, right, if not, let D equal smallest degree of some element H that's in the ring of invariance, but not in the subring generated by the F's. All right, so now we're going to assume that the F's generate the ideal, but suppose they didn't generate the ring. Take a homogeneous element in the ring that's not in the subring generated by the F's, and assume that you've taken it with minimal possible degree. Okay, and now I'm going to claim that gives a contradiction. Okay, why? Well, since so in particular, this degree is not going to be 0, because if it were constant, it would be in the subring generated by the f's. So H is a homogeneous invariant of positive degree. So it's in the ideal. So we can certainly write it in the form sum AI Fi, and without loss of generality, AI is going to be homogeneous also of degree d minus the degree of Fi. Okay. And now here's the key point, I should introduce, in fact, a concept at this moment, which we'll need later. We want to consider, right, so this ring of, by complete reducibility, this polynomial ring in every degree, right, is going to form into a direct sum of irreducibles, and among those will be the invariants. So the ring of invariants is going to be a direct summand of the whole polynomial ring as a representation of G, and actually as a module over itself. But not only is it a direct summand, you can write down very explicitly what the projection is on that summand, and it's called the Reynolds operator, R. So I'm going to define R sub f, R of f, to be the following thing. You just average over the group. So you take all elements of the group, divide by the order of the group, G of f. Okay? So if you take any f, this gives you obviously an invariant polynomial, because once you apply any group element to this, it just permutes the terms in this sum. On the other hand, if f was invariant to begin with, then all these G of f's are going to be f again, and you're just taking this many copies and dividing by this, and you get f back. Right? So this is actually the projection on the invariants. This is the Reynolds operator, and it's a projection of k of v back onto its direct summand, the ring of invariants. Okay, and it's a projection as a G module. It's also a projection. It's a homomorphism of modules over the ring of invariants. In other words, it commutes with multiplication by invariants. Okay, so let's apply the Reynolds operator to this equation. Okay, well, H is already invariant, so the Reynolds operator on H is going to give us back H. The F's are also invariant, so the Reynolds operator on them gives us them back, and the Reynolds operator on the A's is the only thing we're left with. We're going to get H equals some RAI Fi. Okay? But now the Reynolds operator applied to AI is, of course, going to be homogeneous of the same degree as AI was. So, and that degree is less than D. Right? So by induction, since D was a minimal degree for which the subring of generated by the F's didn't give everything, all this stuff is in the subring generated by the F's, and so H has to be as well. Right? All right, so that's the classical proof of this result of Hilbert. Now, oh, that's too bad. That wasn't the right board to write that on. Okay, so in particular from this, you know that the ring of invariants is finitely generated, because the ideal is. And then the next question you might ask is, well, can we say something about what it takes to generate it? For example, can we give a bound on the degrees of the generators? Okay, and there's a classical theorem that goes back to Emmy Noether that gives an answer to that. KVG is generated by elements of degree less than or equal to the order of the group. Okay. Now, the classical proof is in characteristic 0. But the theorem is true in any characteristic as long as you have this hypothesis. And I'd like to discuss a more modern proof just briefly. And it's based on a beautiful lemma due to Harm Dirksen. And it sort of ties together this co-invariant ring and also a subspace arrangement that comes into the picture. So let me just explain that quickly as well. So here's Dirksen's lemma. Okay. This is very nice. So I want to, actually, before I write down this lemma, I better define one or two things. So what Dirksen does is he considers the arrangement of subspaces in V cross V, where you look at, for each group element, you look at sort of the graph of that group element, the set of points pairs x, y, where y is actually g of x. Okay, so let's look at the coordinate ring of K of V cross V. Let's fix some coordinates x on V and y, well, on V cross 0 on the first factor and y on 0 cross V. So we've got two sets of coordinates here. And they should match. I mean, I want the y's just to be the same as the x's only on this second copy, right? And then, so then I can look at, let's say, V sub g is just the set of pairs x comma gy, gx, right? So this is just the linear space defined by the equations that the y's are g of the x's, right? So yi minus, I have to be a little careful here because it's actually, I think it's yi should be g inverse of, no, I guess it's okay. There's some issue about whether it's g or g inverse here, which I don't want to think about. It doesn't matter. So for all I. Yeah, there's some. Yeah, that's right. That's yeah, exactly right. So gxi is the function xi composed with g inverse, right? Which xi composed with g inverse will be. I still don't want to think about it. If I'm wrong, there's a right version, and everything I say will be correct with the right version too. Okay. So all right. I'll put a little question mark there, though, because maybe that's VG inverse. Okay, so Dirksen's arrangement we're going to consider the union over all the g's of the V sub g's, and of course here at this, as soon as you do that, it doesn't matter whether I had G or G inverse, right? So its ideal is, let's call it J, is the intersection of the ideals, and let's call this ideal here J sub G is the intersection of the J sub g's. Okay, and so Dirksen's lemma is a description of this ideal. Or rather, not a description of this ideal, but a relationship of this ideal with the ideal that defines the co-invariant ring. Okay, so basically, in geometric terms, Dirksen's lemma says if you take this Dirksen arrangement, let's call it, right? So this is just an arrangement of order of G subspaces in V cross V. And what Dirksen's lemma is going to say is that if we take this Dirksen arrangement and we set the y's to 0, we scheme theoretically intersect it with the first copy of V cross 0, we're going to get a subscheme of V, and that the ideal of that subscheme is going to be the IG. That subscheme is going to be spec of the co-invariant ring. Okay, so to put that another way, if we take J, and so now J is an ideal, right, in the polynomial ring now in two sets of variables. It's in K of V cross V, which is K of X, Y, right? If I take J, and now I want to intersect with the locus Y equals 0, scheme theoretically, so I just take J plus the ideal generated by the Y's. And now just get, that effectively gets rid of the Y's, but let's do that explicitly by projecting on the x coordinates. So let's intersect this with the polynomial ring in the x's. And now I've got an ideal, right, in K of V. And what is that ideal? It's I sub G. Okay? It's the ideal generated by the homogeneous invariance of positive degree. Okay, so let me also, since none of these lemmas is hard to prove, so let's just discuss that for a moment too. One direction is easy, which I guess is this one, right? No. Yes, this one. So I want to show that every homogeneous invariant of positive degree belongs to this, right? So if F is a homogeneous invariant of positive degree, then f of x minus f of y is a polynomial that vanishes on Dirksen's arrangement. Okay? Because if f is invariant, then if you set the y's to g, for any group element g, if you set the y's to be equal to g of x's, you're going to get f of gy will be the same as f of y, and that'll be the same as f of x when the y's are set to the x's. All right, so this is going to vanish on the Dirksen arrangement. This is going to be in J, right? And on the other hand, mod y, you just get f of x, right? And so that shows that f of x is actually in here. Okay? And the nice part of the argument is to do the other thing, the opposite way. So suppose I have a function in here. So this means it's a polynomial in x that happens to be in the ideal generated by y plus the ideal of stuff that vanishes on the Dirksen arrangement. So suppose I have f of x equals, well, what? Equals something in the ideal generated by the y's, and let's write that as a sum ai of x bi of y. Certainly anything in the ideal generated by the y's can be written this way, with furthermore the assumption that bi of y is not got a constant term. Right? Plus, well, something that vanishes on the Dirksen arrangement, say p of xy. Okay? And now here's the clever idea of Dirksen's. Let's apply the Reynolds operator to this, but let's do it in the y's only. Okay? Excuse me? Oh, for example, I could write this as a linear combination of, right, I mean, the ideal generated by the y's, for example, is spanned by all monomials in the x's and y's that happen to be divisible by 1 over y. If I wanted to, I could actually take this to be a sum of monomials in x times monomials in y that aren't constant, right, with some coefficients. Right? So, yeah, so it's easy to separate the variables. So now I want to apply the Reynolds operator, but only in the y variables, and see what we get. Well, of course, if I apply an operator that only changes the y variables, f doesn't change. So this is not because f is invariant, but actually just because it doesn't involve the y's. Right? And by the same token, of course, the a's don't change. But I get the Reynolds operator applied to the b's. Right? Plus, well, I get the Reynolds operator in y applied to p of xy. And now here's the crucial observation. This is still in J, okay? Because J, right, the arrangement here is unchanged if you act by G on the y coordinates without changing the x coordinates, because the arrangement was the union of the y's being any G of the x's. So if you change the y's by an element of G and you don't change the x's, the arrangement is still invariant, okay? So you can operate on this with the Reynolds operator in the y's, and you're still going to be in J. Okay? And so now I've got f written in this manner. And so this here is the Reynolds operator in y applied to a homogeneous invariant of positive degree, let's say. I mean, we certainly could have taken these to be homogeneous. Right? So this stuff here is clearly an IG of y. And so now comes the key idea. After we do this, right, the left-hand side still only depends on x. Right? So the right-hand side, even though it's got y's in it, secretly also only depends on x. In particular, I can set y equal to x without changing it. Okay? So substitute x for y, and what will happen? Since this expression is still in the ideal of the Dirksen arrangement, it's going to vanish whenever the y's are set equal to, actually, to any group element applied to x, and in particular when the y's are set equal to x. This will go to 0, and this, which was an element of ig in the y's, will become an element of ig in the x's. right? So now I'll have F equals the sum AI of x times Reynolds operator of BI of x. And that exhibits F as an element of the ideal I. All right, so that's Dirksen's lemma. I'm sort of, this is really a clever thing. I mean, I'm amazed by this, even though I think I understand the proof, but when I get done with it, I'm sort of amazed that it works anyway. Okay, so let me give you a third lemma, which is sort of even simpler, which doesn't have a name. But suppose that instead of taking the intersection of the JGs, I took the product there. Okay? So let J prime equal the product for all G of JG. And let's do the same thing as Dirksen. Let's try to figure out what J prime plus Y intersected K of X is. Okay, what's the scheme theoretic intersection of the product of the ideals of these linear subspaces with the 0 fiber in the Y's? It's just exactly the order of Gth power of the ideal generated by the variables. And this is actually easy. Right? So first of all, right, these ideals are generated by linear forms in the x's and y's. So I just want to make an observation, actually. Notice that J prime plus Y intersect K of X can be described in this way. And this is true for any ideal J prime. Right? It's the set of all polynomials in X that you can get as f of x comma 0, where f of x comma y is in J prime. Right? I mean, in effect, what this says is to get this, a sort of canonical representative of this in X, you set the y is equal to 0. Right? So, so this J prime is generated by products of linear forms, as many as the order of the group. And if you set the y is equal to 0, those are products of linear forms as many of the order of the group. So these are homogeneous elements of degree, the order of the group, that generate the thing. So certainly contained, right? And to see the other direction, I just have to show you that anything of degree equal to the order of the group can be expressed in this way, right? So let's just take any monomial, right? Let x to the alpha be a monomial of degree equal to the order of the group, and let's just write it as a product of the variables. xi1, xi2, let's give this number a name, d, up to xid, all right? And let's just enumerate the elements of the group in some arbitrary fashion, g1 up to gd. Okay? And now let's look at the following polynomial. F of xy is the product of xij minus gj of yij. Okay? So this is a linear form in the y's for j going from 1 to d. Okay? So obviously f of x0 is x to the alpha, right? Because the y's just disappear. On the other hand, the jth factor here is in j sub g inverse, I guess. Okay? So this product is in j prime. All right. And if you put these together, you get a nice proof of Noether's theorem, right? Because this shows that, right? So j prime is certainly contained in j. This shows that the dth power of the maximal homogeneous ideal is contained in this I sub g, right? And that in particular implies that Ig is certainly generated by its elements of degree at most d. Okay, but there's an important point here I want to make. You get something stronger, right? What you get is that the coinvariant ring Rg is 0 in degrees greater than the order of the group. Okay, so it gives you a nice kind of picture of where the covariant ring has to stop. All right, so this is probably all I want to say about sort of general relationships between ring of invariance, covariant ring, and things like that.
Was last inequality known before Dirksen? This is strong, then.
Yeah, so basically, I think the proof I've given here is basically sort of a combination of Dirksen's idea and also a recent proof of Fogarty. This should have all been discovered a long time ago, but for some reason it wasn't. But yeah, so Fogarty shows this seemingly stronger statement. Okay, so yeah, so and this, I mean, this, on one hand, this bound is sharp because if G is a cyclic group, then you really actually have minimal generators of degree D, and the ring of coinvariance goes all the way up. On the other hand, if G is not a cyclic group, then it never happens. And there's, so one can ask the question, well, suppose, can you improve this kind of bound by looking a little more closely at the structure of the group? And really very little is known. There are results known, but nothing very systematic about sort of what the ring of invariance looks like, given additional information about the group.
This really says that the regularity of IG is less than equal to D, right? That's the difference.
Yeah. Yeah.
3/4 G is also good.
Sorry?
3/4 of G. 3/4 of G is good. For non-cyclic.
Yeah. Okay. Yeah, and there's some other. I mean, I think there's a criteria. If G is abelian, there's some criterion for exactly what the number is. But in general, it seems to be hard to say much about, particularly the ring of coinvariance, sort of exactly what it looks like for a particular group. And that is sort of what I want to get into now. So, so at this point, I want to return to the situation that we have been discussing in the whole series of lectures. And so now, G is going to be the symmetric group, and V is going to be n tuples of points in the plane. Okay, so for now, V becomes, well, first of all, K becomes C. V becomes E is this set of n tuples of points in the plane. And G becomes the symmetric group, permuting the points. Okay, so our polynomial ring C of E, same notation as last time, is polynomial ring in the x's and the y's. Not to be confused, by the way, if I want to do the Dirksen arrangement, I'm going to need x's, y's, x primes, and y primes, right? I mean, I've already got 2 copies of something inside E, but I'd have to take 2 copies of E for the Dirksen arrangement. So sigma is permuting the variables in the obvious diagonal sort of way. Okay, so that's our action, and we want to ask, what does the ring of invariance and coinvariance look like? Okay, so again, as we did last lecture, I want to first consider the case where the points are on the line instead of on the plane, right? So in this case, our polynomial ring is got only x variables and no y variables. All right. Now, when we looked at the ideal of the coincidence locus, the case of a line was absolutely trivial, and I made a series of 4 statements, all of which were completely obvious, and the only reason for stating them was to lead to their analogs in the general case. But here, the case of points on a line actually is slightly interesting. In a sense, it's trivial in that it's part of a well-known theory. But it's not an entirely trivial theory. Okay, so one thing I want to do is I want to look at the invariants. What are the Sn invariants on this? Well, those are the symmetric functions in the variables x1 through xn. All right, well, there's a classical theorem, the fundamental theorem of symmetric functions, that tells you that the symmetric functions in n variables are generated by the n elementary symmetric functions as a polynomial ring. So this is actually the polynomial ring C of E1 through En, where Ek is Ek of the x's. is an elementary symmetric function. Or you could use power sum symmetric functions or what have you. There's various other choices. Elementaries are nice because it would even be true over the integers. All right, so the ring of invariance is a pretty nice ring in this case. It's a polynomial ring. Once you see that, of course, then this means that the ideal I is generated by these elementary symmetric functions. So it's a complete intersection ideal, right? Because there's n of these, and they generate an ideal I whose, right, the quotient by it is this covariant ring, which is zero-dimensional. So RSN is a zero-dimensional complete intersection ring. All right, and that means we can, for example, immediately write down its Hilbert series. Right? All we have to do is look at the degrees of these generators. Right? The Hilbert series of the co-invariant ring is going to be the product of the degrees 1 minus the degree of the generators divided by 1 minus q to the n. So we're going to have 1 minus q up to 1 minus q to the n over 1 minus q to the n. Okay, well, that's actually a very nice thing. That's the q analog of n factorial. Right? Let's write out what that is. So that last thing is actually equal to what's sometimes denoted this way, nq factorial, which means nq n minus 1q down to 1q, let's say, where kq denotes 1 minus q to the k over 1 minus q, which is, right, q to the k minus 1 plus q to the k minus 2 plus dot, 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 plus 1. Right, so that's a q analog of k in the sense that if q were equal to 1, since there's k terms there, you get k. All right, so the Hilbert series is this q analog of n factorial. In particular, the dimension of this as a vector space, its length as a ring, is n factorial. Okay, and one can say a little more. In fact, as an SN module, as an SN representation, this ring of coinvariance is isomorphic to the regular representation, which is the action of Sn in effect on itself, right? That is on its group algebra, on the linear space formally spanned by the elements. But this is interesting because this has no natural grading, and this, on the other hand, is a graded ring. So you get a graded version of the regular representation of the group. And one can also calculate completely explicitly exactly what that grading looks like. So one can say more. There's a lot of nice combinatorics that goes with this, which I don't want to go into particularly. But one can say that, for example, RSN, if I look at RSN in degree m, let's say, and I form not a Hilbert series, but a sum. So let's look at the multiplicity of, in this, of an irreducible character, v lambda. Okay. So I should say here, the irreducible representations of the symmetric group Sn are indexed in a classical and well-known way by partitions lambda of the integer n. So they're called v lambda. If I look at, in each degree, I look at the multiplicity of a particular representation, and I form a sort of Hilbert series for that, right? Then this is known also. It's equal to what's called f lambda of q. It's a, one can describe it in various ways, but for example, it's the Schur polynomial evaluated in infinitely many variables that are just powers of q multiplied by 1 minus q times 1 minus q to the n. So this is a power series, but it's a power series that's a rational function. And when you multiply it through by this, you get a polynomial. And that's this f lambda of q, which happens to actually count standard tableaus of shape lambda by, with a q to some power, depending on what's called the major index of the tableau. As I said, I don't really want to get into that, but there's a completely precise combinatorial description of this, and so we really know exactly what this ring looks like. And all these facts are kind of, all this is true, so they're similar facts for any G generated by reflections. Okay, so for any G generated by reflections, the ring of invariance is going to be generated by dimension of V elements. So it's going to be a polynomial ring. The ideal is going to be a complete intersection ideal. The co-invariant ring is going to have the same representation as the action of the group on itself, the regular representation. And in principle, one can actually calculate what that looks like in every degree, because essentially the whole polynomial ring will be a free module over the ring of invariance. The ring of invariance of polynomial ring, it'll be a free module with basis any set of elements that form a vector space basis of the ring of co-invariance. And so you can calculate the Hilbert series of the ring of co-invariance from the Hilbert series of the whole polynomial ring, which actually is easier to compute. Okay, so, and generated by reflections, what does that mean? In the case of the symmetric group acting in one set of variables, the transposition ij, right, it sends xi to xj and fixes all the other variables. So this fixes pointwise every point on the hyperplane xi equals xj. Okay? So in general, a linear automorphism that fixes every point of a hyperplane is called a reflection. It's a real reflection if it has order 2, so its eigenvalue on the, its one non-trivial eigenvalue is -1. In general, you're allowed to also have complex reflections, which might have order other than 2. And if G is generated by reflections, you'll have a story similar to this. And conversely, any of these properties holds only for G that are generated by reflections. So there's a whole classical theory of this, which is due to Shepard and Todd, and who in fact classified all these groups that are generated by reflections, and Chevrolet and Steinberg. Okay. So the case of points on a line is interesting, but in a certain sense is sort of just a special case of a well-known general theory, and can be obtained quite explicitly by rather elementary methods. All right. So now I want to compare that, just as we did with the last time we talked about the ideal of the coincidence locus, compared the case of points on a line with the case of points in the plane, and I want to do that here as well. So I want to see how much of this goes over. Well, in some sense, none of it does, but what does go over, and what's a bit of a surprise, I guess I'll just keep this down here. What does go over is that it's possible to describe the ring of invariance and co-invariance quite explicitly. Okay, so now we're going to turn to the case that we're interested in, which is V equals E equals C2n, and our ring is C of xy. Okay, so first question we might ask is, what does the ring of invariance look like? Okay. Well, in fact, this is pretty easy, and there's an old theorem of Haiman-Weil that gives the answer. It's generated, but not freely as a polynomial ring, of course, because there's going to be too many generators. But it's generated by elements PRS, 1 less than or equal to R plus S less than or equal to N, where PRS is what's called a polarized power sum. It's the sum I equals 1 to N, xi to the R, yi to the S. Okay? Obviously, it's invariant if we permute the variables. Okay? It's homogeneous of degree R in the x's and S in the y's. And so it's an analog of the, if you just had one set of variables, you'd just have power sums, and those would generate. This is a kind of two-variable analog. All right? So these generate the ring of invariance. In fact, they generate it minimally. So these are minimal generators. And this is a theorem of Haiman-Weil. And it's also true in any number of sets of variables, x, y, dot, 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 z. Okay. You can find this in his book on the classical groups. However, beyond this, actually, there's not much known. So, right, so it would be natural to ask, well, if that's a minimal set of generators, let's try to describe the ring more fully with respect to those generators, right? What are the syzygies among them, for example? Can we maybe even give an entire free resolution of this ring as an algebra over the polynomial ring in these generators? So those things seem to be unknown. Syzygies, maybe a whole free resolution. In any case, it's certainly a Cohen-Macaulay ring. That's the Hochster-Roberts theorem that this is true for any reductive group, certainly for a finite group in characteristic 0. In the case where, so let me just make a remark here. All right, so by Hochster-Roberts, this ring of invariance is Cohen-Macaulay. And that would be true in any number of variables, but it's actually in two sets of variables. It's a little more special because it's Gorenstein. And that's because in two sets of variables, every element of the symmetric group is acting by a linear transformation of determinant 1. And in general, the canonical module of this ring of invariance is always the ring of covariance, the elements that for which the group acts by the determinant representation. So if the determinant representation happens to be the trivial representation, it's Gorenstein. So that's because Sn here is acting as a subgroup of SL E and not just GL E. And by the way, why is it doing this? Because a transposition is now going to interchange xi with xj, but it's also going to interchange yi with yj. If it only did this, it would have determinant -1. But now it's acting on two copies. It's going to have determinant -1 squared, right, which is 1. And of course, the group is generated by the transpositions. Okay. So more generally, this will be Gorenstein when there's an even number of sets of variables. Of course, it happens to be Gorenstein when there's one set of variables, but for the wrong reasons. Okay. This is a fake Gorenstein ring. Okay. In precisely the sense that its canonical module actually comes canonically with an action of the symmetric group, and it's not the trivial action. So it's Gorenstein, but with a non-trivial action of Sn, with an action of Sn by the sign representation on its canonical module. Okay, so, and one can write down the Hilbert series also. Which is easy also because you just count the basically, a basis for these invariants is given by just take any monomial and then just look at the sum of all permutations of it. So then you can just count them. And you get a nice description. If Hn is the complete homogeneous symmetric function of degree n, then you get Hn evaluated in 1 q squared, comma dot t, qt, q squared t, comma t squared, qt squared, et cetera, like this. So all products of a power of q by a power of t, take that infinite alphabet of variables, take the complete homogeneous symmetric function of all that. It's a power series, but it's actually a rational function of q and t, and that's the Hilbert series.
What's the complete homogeneous symmetric?
Oh, so this means this is the sum of all monomials in these things of degree n. And this is, all, again, if you had more sets of variables, then you just have q1, q2, q3, and so on. Okay. So the invariant ring is not too mysterious. Okay. But the co-invariant ring is another story. Actually, I guess I have this one. So what about R Sn equals C of xy mod the ideal generated by the positive degree invariance? And we know what that is, by the way. It's generated by the PRSs. Okay, so a priori, there's sort of no reason to expect this ring to have any nice behavior. Right? Really, the only general theory that says co-invariant rings are nice is this Chevalley-Steinberg-Shepard-Todd theory for reflection groups. There is no, really, there's no other general theory about groups that have nice rings of co-invariance. So this comes as a little bit of a surprise, and certainly came as a big surprise to us. Garcia and I, in around 91, we were studying a problem on Macdonald polynomials that the details of which are not important, but it led us, for various natural reasons, to think about this ring, because we were looking at some spaces that were naturally quotients of this ring. We thought maybe, maybe if we understand this ring, we'll understand something about these spaces. So we put it on the computer. You could very easily do this, right? You know the set of generators, so you just get your favorite Grosvenor basis box, and you put these generators in, and you find a basis, a vector space basis for what's left over, using Macaulay or something, and then you just see how many there are. Okay? And it turned out that a miracle occurred. So so it was a conjecture for a long time, but eventually it's become possible to prove this using the connection of this all with the Hilbert scheme. So the theorem is that the dimension of RSN as a vector space, so of course it's zero dimensional as a ring, so the only interesting invariant here would be its length. Its dimension, right? So if there were one set of variables, it would have been n factorial. In two sets, it's n plus 1 to the power n minus 1. Okay? Now, this is a drastically striking combinatorial number. Okay? It's the number of rooted forests, for example, on n labeled vertices. Okay? This and the Catalan number are just about the most important combinatorial numbers you can have. Okay? And Catalan numbers are in here, by the way, also. If you look at the dimension of its, so Sn, of course, acts on this ring, and if you look at the alternating part of it, it's the Catalan number. Okay? 1 over n plus 1 times 2n choose n, the same Catalan number we talked about last time. Okay? And it is the same Catalan number we talked about last time because it's an easy proposition that any set of polynomials whose images are a vector space basis in here are also minimal generators for the ideal generated by the alternating polynomials. Okay? So this, in fact, the reason we know that the minimal generators for the ideal I we talked about last time, that the number is the Catalan numbers, is because actually we know what this ring looks like. From the Hilbert scheme, in fact, there's a formula in terms of Macdonald polynomials that gives the character of Sn acting on this in every degree. And this is doubly graded, so that's every bi-degree. I don't want to get into that formula, but I will mention a couple of further consequences of it because it gets sort of more interesting the more closely you look at it. So, for example, suppose I were to look at the whole action of Sn on it. Right? Rsn is isomorphic as an Sn module to what? If there were just n variables, if we're doing points on a line, it would be isomorphic to the regular representation, as we said, to the action of Sn on its own, on itself, on its own group algebra. Here it turns out to be isomorphic to something also quite neat and more interesting in a way. So it turns out to be, first of all, there's a lot of copies of the sign representation, so it turns out to be isomorphic to the sign representation tensor to simpler representation, which is a permutation representation on a finite set. And the finite set is Q mod n plus 1 Q, where Q is the abelian group z to the n mod z with this middle, this z you're quotienting out being generated by the vector of all ones. Okay, so let me just explain what I just said. Okay, so, all right, so z to the n is an abelian group. In it, there's the subgroup generated by the all ones vector, which I'm going to mod out. The symmetric group acts, of course, by just permuting the coordinates in the vector. That's a fixed vector, so I'm modding out something invariant, so Sn still acts on this quotient group. Right? Then I take Q mod n plus 1 Q, which is, so this is still an infinite group. It's a free abelian group of rank n minus 1. Modded out by n plus 1, I get a finite abelian group of size n plus 1 to the power, the rank of this free abelian group, which is our n plus 1 to the n minus 1. And Sn still acts on it. Okay? So Sn acts on this finite group as a set. Then I take the linear representation of Sn by just taking a vector space which has the elements of this set as its basis, Sn permuting them in this way. This is now a permutation representation of this dimension, and just tensor it by the sign and you get that. Okay.
I don't understand. These are algebras, right? What does tensoring with the E mean?
This means tensoring as a vector space, but as an Sn representation. So it just means that, right, whatever an element of the group did here, it's going to do the same thing here, only times -1 to the sign of the permutation. Okay. So, yeah. So this is amazing. And it's even more amazing if you realize that what this is the root lattice of type an-1, for which the symmetric group is the Weyl group, which might lead you to suspect there's something like this for other Weyl groups, and there sort of is. Okay. What else should I say?
Let me ask you a question about the previous. The degree of PRS, if I understand right, is R plus F.
Yes.
What's the regularity of this idea?
I don't know. I don't know.
But since you know the Hilbert function, you know which degree it vanishes. RSN vanishes in, which is the regularity.
Oh. Well, wait a minute. I know.
At least.
Okay. Yeah, I see what you're saying. Yeah, that's right. Of course. Yeah. I'm sorry. I was thinking you were asking about the ring of invariance. No, right. That's right. The ring of coinvariance. Right, and this is worth mentioning. I meant to mention it, in fact. Of course, we have this sort of global bound that says this would vanish above degree equal to n factorial, which is the order of the group. In fact, the highest non-zero degree in here is n choose 2. Okay. So, right, so that's the answer to your question. The regularity equals n choose 2.
The one copy of the symmetric group is at n minus 1 choose 2?
In one copy of the symmetric group, it's also n choose 2. Because, so what will happen basically is, right, I mean, in this, if you look at the y degree 0, if you just set the y is equal to 0 in here, you get back the one you had before. All right? And they both go all the way up to n choose 2. It's just that this one sort of goes across diagonally from there. Okay, so maybe I won't really say anything more about this. There is a nice, this is the number of rooted forests on n-labeled vertices, and if you, I'll say one more thing. If you look at a generating function, so this has, as it's doubly graded, and one thing we don't know actually is a combinatorial interpretation for the double grading, although there's a formula. But if I look at one grading, r comma blank, I look at degree r in the x's and I ignore the degree in the y's, times q to the r. It turns out to be the sum over f equals a rooted forest on n-labeled vertices. I'll just write f equals forest of q to the number of inversions of the forest, which is some nice combinatorial statistic that I'm not actually going to define because I want to just take 1 minute to mention sort of questions. So again, there are lots of open problems here, and let me just close by mentioning some of them. So you can ask, what about other groups? And here it seems quite reasonable that really what you should be looking at is what about other Coxeter groups, at least, maybe other complex reflection groups. Okay. And there's an important thing here. These kinds of things are derived by using this Hilbert scheme, which what it does is it gives us a desingularization of C2n mod the action mod Sn. For other Coxeter groups, you want to again look at them acting on two copies of the defining representation, then you want to look at the quotient singularity. But for some of them, there is no nice resolution of that singularity like the Hilbert scheme. The technical term is Crepant resolution. Sometimes these don't exist. So there's really no hope of sort of repeating the same methods that give these things for some of the other Coxeter groups. But nevertheless, one can conjecture falsely that the dimension of this ring of coinvariance would be, this is the Coxeter number plus 1 to the rank. That conjecture is wrong because this ring is a little too big and you should mod out a little bit more. You should mod out enough to make the socle carry the sign representation, which already happens for the coinvariance in Sn. then the conjecture seems to be right. In any case, you can make sort of the weaker conjecture that there exists a natural quotient of this with this dimension and various other properties like having this representation. And there's a lovely preprint that just came out by a fellow called Ian Gordon. Ian, spelled that way. What did he show? Sort of a weak, yes. Okay. So you can't take the full strength of this, but there's sort of slightly weaker analog, and he showed that it holds for all Coxeter groups, which is really nice, and not using any sort of Hilbert scheme techniques. So this is the first evidence that it is possible to get results like this without resorting to the Hilbert scheme. That's one problem I wanted to mention, but there's a lot of room for strengthening that. In particular, he doesn't have an answer for complex reflection groups, only for Coxeter groups. And the other thing I want to mention is, remember last time we talked about the ideal of the coincidence locus being a free module in one set of the variables. Okay? I think it's probably true that for this situation, so let me state it as a conjecture, Dirksen's arrangement let's say W, so this is now an E cross E, right? So its coordinate ring, C of W, right? So this is a quotient of the polynomial ring in X, Y, and X prime, Y prime. Okay, mod some ideal. All right, and the conjecture is that this is a free module in one set of the original variables. I don't actually know how to prove that using the Hilbert scheme, but if true, it would have it's equivalent to a certain Schief-Cohn-Malachy vanishing theorem for the Hilbert scheme that I suspect is true and would be very nice to know. So I think I'll just leave it at that.